In this next chapter, we're going to take some time to look at some other ways of factoring or solving quadratics and how we can use these methods to solve other types of equations and polynomials as well. So in the past, when we've had a quadratic in standard form as shown here, we've had to rely on the factoring technique in order to solve it. And if it was a prime polynomial, then we were kind of at a loss for how to solve the equation. We weren't able to go any further. And so, what if we can't factor a quadratic? How do we solve it? Well, we have three other methods that we can use: square root property, completing the square, and the quadratic formula. These all have their own special place and time where we're going to use them depending on the structure of the equation. And what I really encourage you to do is focus closely on the structure of the equations and how they relate to the problems that we are using or the method that we're using to solve them. So we'll start with our square root property. Consider the equation x squared equals 9. Rather than factoring, we want to think about how could we isolate the variable. Well, in order to get the squared to be gone, if we think the inverse of what we did with our radical equations, instead of squaring both sides of the equation, we can square root in order to get rid of the exponent. That leaves us with x equals 3. But we have to think about, does that represent all possible solutions to my equation? Let's also consider x plus 4 squared equals 9. Again, I can square root both sides, eliminate the radical. I have x plus 4 equals 3. And then we can subtract 4, and we get x equals negative 1. But again, does that necessarily represent all of the possible solutions? And same thing here. Before we can square root, we need to subtract 3 from both sides, giving us x squared equals 9, and then we had the same situation that we had over here where we could solve. So let's think about x squared equals 9. We found a value of 3, and we know that 3 works because if I square 3, that does indeed give me 9. However, is 3 the only number that I can square and get a value of 9? Well, it's not. I could also square negative 3. If I square negative 3, I also get a value of 9. And remember that when we take square roots, we have what's called the principal root, and we also have the negative root. The same thing holds true for this equation up here. We can plug in 1, and we know that 1's going to work, or negative 1. But would 1 work, or some other number also work in this second equation? So if we plug in negative 1, we get 3. 3 squared is 9. But what if we plug in a different number like a positive 1? 1 plus 4 is 5 squared. That's not 9. So we know that 1 doesn't work. But is there another number that when we go ahead and add 4 and square it, do we get 9? Well, think about if we had this expression equal negative 3. Well, in order to have it negative 3, x would have to be negative 7. Negative 7 plus 4 equals negative 3, and then negative 3 squared equals 9. So we have to have an easier way to find this solution. Let's go back to those types of roots. If we have a radical, if b is a real number, and we have a squared equals b, if we go ahead and square root both sides, then a has to be both the principal and the negative root of whatever b equals. So let's take that back to our earlier examples. If I have x squared equals 9, I square root both sides. X equals positive and negative square root of 9, which means x equals positive and negative 3. If we go to our second example, x plus 4 squared equals 9, we square root both sides. X plus 4 equals the principal and the negative root of 9. That means that x plus 4 equals positive and negative 3. And since we have to continue evaluating, we can solve both of these equations. X plus 4 equals 3 and x plus 4 equals negative 3, leaving us with negative 1 and negative 7. And we saw earlier that those two values are the solutions for both equations. So when we apply our square root property, we need to consider both the principal and the negative root in order to get all of our solutions. So let's apply that to a couple examples. Here we have x squared equals 50. I can go ahead and square root both sides. X will be the positive and negative square root of 50. Since 50 is not a perfect square, we need to simplify it. 25 and 2 are two good factors to use. So x equals the positive and negative square root of 25 times the square root of 2, which is positive and negative 5 square root of 2. Now remember, this counts as two answers, 5 square root of 2 and negative 5 square root of 2, but the shorthand is sufficient to use in this case. Here, we can't square root this yet because we've got this minus sign and these aren't perfect squares. We can't really simplify that. So let's isolate this term first. We can add 14 and then divide by 2. And now we can go ahead and square root both sides. X equals the principal and negative square root of 7. Since we can't simplify radical 7, we leave it alone. We can square root both sides. That eliminates our squared. X plus 1 equals the principal and negative root of 12. Factors 4 and 3. That gives us plus and minus 2 square root of 3. And then we can subtract 1. X equals the principal root and the negative root of 2 square root of 3 minus 1. Now since these aren't like radicals, I can't actually subtract them. And so we can't simplify any further. And since we can't simplify any further, standard dictates that we actually put the rational term in the front and leave the operations in the middle for our shorthand. Negative 1 plus and minus 2 square root of 3. We can use that as our shorthand, but remember that this represents two distinct numbers that will have drastically different values. Negative 1 plus 2 square root of 3 is approximately 2.46, while negative 1 minus 2 square root of 3 is going to be approximately negative 4.46. So drastically different numbers, but again, this shorthand is perfectly acceptable to use. Our last example, when we go ahead and square root, we notice that we have a negative. That means we're going to have a complex solution. So we have 2x minus 5 equals the principal and negative root of negative 16, which is 4i. And then we can go ahead and isolate our variable. Since we're going to add 5 to both sides, we're going to put the rational real term in the front, plus or minus 4i. Then we divide both sides by 2. X equals 5 over 2 plus and minus 4i over 2. And then we can simplify 5 over 2 plus and minus 2i for our complex solution. Take an additional moment to think about and kind of compare how we solve these equations and the structure of the equations compared to standard form when we've tried to factor. So what is the most notable difference between a quadratic and a standard form and all of these equations that we worked up here? So we want to take a moment to think about what's a major difference between the structure of standard form versus the structure of each of these equations. Well, notice in each of these equations, we only have one term with a variable. One term, one term, one term, one term. Only one term has a variable. However, in standard form, we have two terms, the squared term and the linear term. Well, our square root property only works if our quadratic equation has only one term with a variable. And so that means that our square root property is a little bit limited in when we can use it. We have to have these special types of equations in order to use the square root property. And if it's not written in that form, then we can't use it. And to be perfectly honest, a lot of times we won't get quadratic equations written in this form. But that doesn't mean that our square root property isn't very useful, because it's going to be very closely embedded in our next solution process, which is completing the square.